Good morning, class. This is Dr. Hill on audio. If you look at week 12, we were finishing scalar products and we wanted to look at the complex case, the Hermitian case. When the scalar field K is the complex numbers C, the scalar product axioms are a little different. The first one, HP1, where we commute the scalar product, the commuted version has to be conjugated with the complex conjugate. Number 2 is the same distribution. Number 3, if you factor out a complex scalar on the second factor, you factor it out as a complex conjugate, as you see. Example 3, when the vector space is Cn, and we have two vectors, x, y, in Cn, then the scalar product is sums of products of corresponding components. However, the y components have to be conjugated. Everything else is the same as the real case. And we have the same theorems, 2.4, corollary 2.5, theorem 2.6 and 2.7 that we had before the COVID-19 lockdown. Now, when you have an orthonormal basis, E1, E2 through En, for Cn, then the scalar product of VW is simply the ordinary dot product of x and y, where x and y are the coordinate vectors of V and W relative to the orthonormal basis. Homework 10 is page 111, 112, 1 and 4, the GSOP. Number 4 is using the scalar product as the definite integral from 0 to 1. Section 5.3 is applications to linear equations. We've already discussed the rank of a matrix for the matrix version. We know that the rank of a matrix is the dimension of the column space or row space of a matrix, which translates as the number of non-zero rows in the row-reduced echelon form. The solution set to AX equals 0 vector has three interpretations. First, it consists of all solutions to the linear vector equation x1 a1 xn a superscript n. Second, if W is the row space of A, then the solutions to AX equals 0 is W perp, the orthogonal complement of W. And Kn is the direct sum of W perp with W. Third, if L sub A is the linear map going from Kn to Km, then the solutions to AX equals 0 is the kernel of L sub A. And we have our usual theorem 3.1, where if W is a subspace of Kn, then the dimension of W plus the dimension of W perp equals n. Homework 11 is page 117, 118, numbers 1H, 4C, and 7, and the hint for number 7 is the matrix version of homework 6, number 4, on page 63. Next, we look at section 5.6, the dual space of a vector space. The dual space of a vector space is the space of all linear maps going from V to K. Now we're going to use a new word for a linear map. We're going to call it a functional. And so the dual space of V is the space of all functionals going from V to K. When V has finite dimension n, and B, V1 to Vn, is a basis for V, then V, of course, is isomorphic to Kn, as we've already seen. So without loss of generality, we can let V be Kn. Example 0. We find that if A is a vector in Kn, with phi of x equal ax for all x in Kn, then we note that phi equals L sub A, and now Kn is isomorphic to V star. Theorem 6.1 tells us that the dimension of V star is the same as the dimension of V. Example 1. If we let phi sub I be the functional going from Kn to K, be the projection map of Kn onto K, where phi sub I of x equals x sub I for all x in Kn, these are called the coordinate functions for V star. So now for each I, if we let phi sub I be defined by phi sub I Vi is 1, and phi sub I Vj is 0 when I is not equal to j, then the phi sub i's form a basis for V star called the dual basis of V star. Page 128. Now let V be a vector space over K with scalar product. For each V in V, let L sub V, V to K, be the functional in V star defined by the scalar product of V with W for all W in V. It's easily shown that L sub V is a linear map. Theorem 6.2. If the scalar product is non-degenerate, very important, non-degenerate, then the mapping that takes V to L sub V is an isomorphism of V onto V star. Proof. We must show that this is a bijective linear map. We've already noted that it's a linear mapping. To show that it's one-to-one, we have to show that the kernel is trivial. So what is the kernel? Well, it's the set of all V's in V where the inner product of V with W is 0 for all W in V. But since we have a positive definite scalar product, this is only true if V is the zero vector. Hence the mapping is injective or one-to-one. Now, since the dimension of V equals the dimension of V star, and we know from our dimension theorem that dimension of V star equals dimension of the kernel of V star plus the dimension of the image of V star, we immediately get that the mapping is surjective or onto, hence V is isomorphic to V star. So homework 12 is page 131, numbers 2, 3, and 4. Hence, for number 3, you want to take W as the span of the given vector 1i, 0, where W perp is the set of all vectors x in C3 perpendicular to the scalar multiples of 1i, 0. You can just simply take C or alpha to be 1 to simplify what you see on your screen. So if alpha is just 1, then you're looking at the case where you have x plus yi plus 0z equals 0, or where yi equals negative x plus 0z. That means that x and z are independent parameters. So you can take x to be 1, z to be 0, where we get a is 1 negative I 0. And if we take x to be 0 and z to be 1, we get b to be 0, 0, 1. So you simply have to show that AB is a basis for W perp. And then for number 4, take phi to be the functional going from v to k and show that the dimension of the kernel of phi equals n minus 1. To do this, we show that the dimension of the image of phi is equal to 1. Well, we can do this by defining v sub x, where x is an element in k, to be x over phi of v times v, and then show that phi of v sub x equals x. This proves that the dimension of the image of phi is 1, which implies dimension of the kernel of phi is n minus 1. Till next time, this is Dr. Hill saying be safe and take care.